Welcome. In this video, I'll show you how to solve problem 2.47 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem asks us the following. It says, considering the moving delta function well, which is the potential that we see right here, where v is the constant velocity of the well. Part A says, show that the time-dependent Schrodinger equation admits the exact solution of this wave function right there, where the energy is minus m alpha squared over 2h bar squared is the bound state energy of the stationary delta function. The hint they give us is plug it in and check it. And then part B says, find the expectation value of the Hamiltonian in this state and comment on the result. So let's begin with part A. Now this part is simple. It is not necessarily easy, but it is quite simple. All we need to do is plug this into the Schrodinger equation. So the time-dependent one, of course. This is minus h bar squared over 2m d psi dx squared. Now this is, of course, depending on x and t, plus the potential times the wave function. This is equal to, and now instead of the energy, let's write it as IH d dt, right? This is the time-dependent Schrodinger equation, so we need to treat it as such. Okay, so this is what we need to plug everything into. The potential, of course, we already know, but what we don't know yet is the time derivative and the x derivative. So let's calculate those. So the time derivative of our wave function, let's see, so our wave function is right here. Now notice that it is comprised of only exponentials. And when we take the derivative of an exponential, we're going to get the same exponential times the derivative of what is inside of the exponent. So basically, we get psi times the derivative of the exponent. Now, what is the derivative of the exponent? So we have t inside of this exponent and here. So in the first one, we get minus m alpha over h bar squared times the time derivative of the absolute value of x minus vt, and we will find out what this is in a moment. Then we have in the second term minus I over h bar times, and let's see, then we have e plus 1/2, so e plus 1/2 mv squared. The velocity here is a constant, so it doesn't depend on time, so we don't need to worry about it. And then this t becomes 1 when we take the derivative, and this x part, it doesn't count anymore, it has no time. Do I have the correct amount of parentheses? I think I do. Okay, so the question is, how does this thing here, so what we need to determine now is what is the derivative with respect to time of the absolute value of x minus vt. Now, this is not as simple as it looks, but it's also not very difficult if you approach it in the right way. And that is something very important to understand. And it's one of the main takeaways when you're studying physics. Often, you can solve a problem just by asking the right questions. So, what is this derivative? Now, of course, there are two cases. If x is greater than vt, then that situation represents the dt of x minus vt, which we know will give us minus v. But if x is smaller than vt, then we need to add a minus sign to correct for that situation. So we get minus x plus vt, and our derivative is v. So what this tells us is that this derivative will start out, right, if we think of it like here in space, so this is basically the derivative, and this is x, then all the way until vt, this has the value v. So it is v, and then at some point, which is vt, we don't know what v is or what t is, but at some point, then this changes to minus v. So that is what the derivative looks like, right? And now this might look familiar. If not, don't worry. There exists a function that is called the step function or the Heaviside function, which what it does is that this, let's use z, right, just some other variable so we don't get it confused. This function has a value of 1 whenever z is greater than 0. So the z is basically the condition, and it is 0 and if that is not true. So how can we use this? Because think of the situation that we need to represent. So we want the derivative, so d dt of x minus vt. This starts off as v, and this is a very good way of thinking of the Heaviside function when it comes up. Sometimes you have to build functions that include it, and it can be a little bit hard. So we start off with v, and at some point we need to go from v to minus 2v. So at some point we need to add minus 2v. But this isn't at all points. This is only once our condition is met. This is only once we have surpassed this point right here. Right? It is only in this side, not on this side. So we need the step function to tell us when to turn this on. Right? So by writing it like this has a value of 0 unless x is greater than vt. And in that case, it has a value of 1. So let's check this. So if we are in x smaller than vt, then this is 0, and our derivative is v, which is exactly what we want. And if we are in x greater than vt, then this has a value of 1, and we get v minus 2v, which is minus v, which is exactly what we want. So there we go. This is the derivative that we were looking for. So now we just plug it into the expression for the derivative with respect to time. So let's see. We have, and well, maybe let's factor it out a little bit so we can make it just a bit more compact. So we can factor out v and maybe a minus sign. We get minus v factor of the step function x minus vt times 2 minus 1. There we go. So now let's plug it in. So the derivative with respect to time of psi x comma t, this is our wave function, and then we get minus m alpha h bar squared times minus v times 2 theta, or step function x minus vt minus 1 minus I over h bar, and then e plus 1/2 mv squared. I forgot a parenthesis there. It doesn't really matter much, but okay. And of course, we don't want to just put this into our wave function. We want to put IH bar into the wave function. So for that reason, let's just multiply this by IH bar. So IH bar. When we do this, well, we can also simplify a little bit. So these two minus signs cancel each other out, and we'll get an A right here, and the H bar will cancel out the square here. And then in the other term, the i's will cancel out, so this goes to plus 1, and this h bar just goes away. So we simply get plus. Okay, there we go. Now we want to calculate the second derivative with respect to x of our wave function. I'm gonna pull this to the side and just do it like this. Okay, so of course, let's begin by taking the first derivative with respect to x. Now, just as before, this entire thing are mainly exponentials, so we will get our wave function back times the derivative of the exponents. So in this first one, we get minus m alpha over h bar squared times the derivative with respect to x of absolute value of x minus vt. And then we get minus, now this entire part doesn't have an x, but the second one does. So minus minus, we get plus I over h bar mv. Okay, so here once again we run into this little problem. We have x minus vt absolute value. So now we need to find this derivative. It is no longer derivative with respect to time, but now with respect to x. But the logic will be exactly the same. So let's go for both cases. If x is greater than vt, then we get that the derivative with respect to x of x minus vt, this is simply 1. And in the other case, when x is smaller than vt, then we get that the derivative with respect to x, this is going to be now minus x plus vt, which gives us minus 1. So this is quite similar. Now let's apply the same logic as before. Basically what this means is that the derivative, so let's do a sketch, so just to make it easier to understand. So this is the derivative with respect to x, and this is x. So, and whenever x is smaller than vt, so there's going to be some value vt, we don't really know where it is, but it doesn't matter. Whenever x is smaller than this case, then the derivative is minus 1. But then at this point, it goes up all the way to 1. So this is what we need to build. And again, we are going to have to use the step function. So the derivative with respect to x of x minus vt, this is minus 1, but then at some point it needs to go to 1. So we need to add 2, but only when our condition is met. So only when theta, or basically when x is greater than minus vt. So again, let's check. So whenever x is smaller than vt, this is 0, and we get that the derivative is minus 1. But when x is greater than vt, this turns on, it becomes 1, and we get minus 1 plus 2, which is 1, which is exactly what we need. So this is our derivative. So we can now plug it in, maybe somewhere down here. So we get the psi dx. This is psi times minus m alpha h bar squared. And then the derivative, which is minus 1 plus 2 step function x minus vt, and then plus I h bar mv. And another one. There we go. So what do we have here? Wait, I think I'm missing a parentheses. Yes, I'm missing a parentheses. So maybe like this, and yeah, this one shouldn't be there. Okay, there we go. Now let's take another derivative, right? We want second derivative of psi with respect to x. Now, when we take, this is basically the psi dx times, so this is what we just have. Take a look at this. What we have here is the psi dx, and now when we take the derivative, we will get this thing derived times what we already had, which is this parentheses. But we know what when we take this, we get psi times the parentheses again, so we get this parentheses squared. And then we have psi times the derivative of this parentheses with respect to x. So that is what we will have. So d squared psi dx squared, and now this is psi times this parentheses squared, so minus m alpha over h bar squared minus 1 plus 2 theta x minus vt plus I mv over h bar. And the second part is now plus psi times, and now the derivative with respect to x. But the only x appears in here. Nothing else contains an x. So we get minus 2m alpha over h bar squared times the derivative with respect to x of the step function. Now, the derivative of the step function, what is that now? I'm not going to prove it rigorously now, but I'm just going to give you an idea. Okay, I spoil it. So we know that the step function for some z is going to be 1 if z is greater than 0, or 0 if z is less than 0. So how does this change as that changes? What is d theta dz? Well, it is 0 everywhere except at z equals 0. So it is delta of z, right? It is 0 everywhere except at z equals 0. This is, of course, not a proof. I'm just giving you a little bit of an idea of why this is the solution. If you're interested, there's a problem in Griffiths where we have to prove it. If you're interested, we can maybe just let me know and we can add it later on. So the point is that this thing right there is simply going to be the delta function of x minus vt. Okay, and there we go. And this thing, of course, is squared. I had forgotten to add it. So let's now expand this square. So we get d squared psi dx squared, and then psi. Okay, and now we have this first part squared, which gives us m squared alpha squared h bar to the fourth. And then we have 1 minus 4 times theta, or well, the step function x minus vt, plus 4 times the step function x minus vt squared. But notice that the step function has either value 1, in which case 1 squared is the same as 1, or it has the value 0, which squared is also 0. So that means that the step function squared is the same as the step function. So that means that this part, minus 4 times step function plus 4 times step function squared, that is the same. So we don't need to worry about it. They cancel out. And that means that we have, okay, so we only have this part surviving. So basically we now are left with this. Okay, and then we have the cross term between the product of this, well, all of this and this. So we get minus 2 times m squared. Then we get IV alpha divided by h bar cubed. And then 2, the step function, minus 1. And finally, this part squared, which is minus m squared v squared over h bar squared. And then we add that. So minus 2m alpha over h bar squared, delta of x minus vt. But we don't only want to find delta squared psi dx, oh, it's not delta, the second derivative with respect to x. We want to find minus h bar squared to m times that second derivative. And that we will then plug into the Schrodinger equation. So for that reason, let's now take this and multiply by minus h bar squared divided by 2m. So let's now multiply this result. So we get psi, and the first part now becomes minus m alpha squared divided by 2h bar squared. This part becomes plus, then we have miv alpha divided by h bar times 2 theta of x minus vt minus 1. And then we have plus mv squared over 2 plus alpha delta x minus vt. So there we go. And this we now want to plug into the Schrodinger equation. And because I'm lazy, I'm just going to start it right here. So let's plug it into the Schrodinger equation. So this now plus the potential times the wave function. But the potential is minus alpha. So this is minus alpha delta of x minus vt times the wave function. And then we have this is equal to IH bar ddt, which we already found. So let's now move it. So this goes there. So there we go. This is now the Schrodinger equation with everything plugged in. And this, if the wave function is a solution, then this should be the same. Now, let's see. We have this and this that cancel out, mv squared over 2, mv squared over 2. We have im alpha over h bar times v times this thing, which is the same as this. So they cancel out. And we are left with minus m alpha squared divided by 2 h bar squared psi is equal to e psi, right? We have the e here and this part. So if the energy of the state is m alpha squared divided by 2h bar squared, then the state is indeed a solution. And this is exactly what they say. So the energy is indeed that. So we have now checked that the bound state, that this solution is indeed a bound state, and we even found the energy. So there we go. Now what we want to do is part B, where we have to find the expectation value of the Hamiltonian in this state. Okay, so we want to find the expectation value of the Hamiltonian, but we know that the Hamiltonian acting on psi is the same as E acting on psi. So if we take the expectation value of this, we get that the expectation value of the Hamiltonian, this is the same as just E. But what is E? E is IH bar d dt. So we want to find the expectation value of IH bar d dt, right? This is something that we already knew. This is just a quick reminder. So what is this? Well, this means that the expectation value of H, this is integral over the entirety of space of psi conjugate times IH bar d dt psi dx. And what is the psi d, or the time derivative basically? That is exactly what we had right here. So this is the time derivative. We already used it, right? So let's take it and wait, did that not work? So let's move this. So that right there is d psi dt. So d, actually like this. So d psi dt is precisely that. So let's plug it into the integral. So minus infinity to infinity. We can take the IH bar. Well, actually the IH bar is already inside. Actually, we already used it here. So this is IH bar. So this is psi conjugate times psi times Im alpha h bar v times 2 step function of x minus vt minus 1 plus e plus 1/2 mv squared dx. So that is what we now want to calculate. So these are two integrals. One is going to be this one, of course. We can take the constants outside. And then we have integral from minus infinity to infinity of, and now we have this 2, so 2 times, now the step function x minus vt psi conjugate psi dx. And we have this minus 1 still, which I will treat separately. So let's take a look at this part first. So then we still have minus infinity to infinity of, and then we have, well, psi conjugate psi dx. So this is the same as this. Now, what is the step function? Again, the step function is 0 if x is smaller than vt, and it is 1 if x is greater than vt. So this integral is the same as the integral from vt to infinity, right? It is the exact same thing because everything before this doesn't contribute at all. It is something relatively similar to what where is this? There. To what the delta function does to the integral, right? It eliminates a part of it, except that the delta function eliminates almost all of it, and this eliminates just a part of it. So now we need to find psi conjugate psi, right? But that is relatively easy because take a look at this wave function. We have one part that is complex, this part right there. So when we take the complex conjugate, that will cancel out. So psi squared will be m alpha divided by h bar squared, and then e to the minus 2 m alpha x minus vt divided by h bar squared, right? This is the absolute value, don't forget about it. So let's plug this into the integral. So this is m alpha over h bar squared e to the minus 2m alpha x minus vt over h bar squared. and dx, of course. So that is the first integral, and well, the second one is the same, right? We have to plug that in, so minus, and this integral is from minus infinity to infinity of e to the minus 2m alpha, absolute value of x minus vt over h bar squared, and dx, and the constants are here, so m alpha over h bar squared. And this, of course, is going to be 1 if the function is normalized. We haven't checked, so maybe this is a good time to check. So is the wave function normalized? So this first integral, we can now use y is equal to x minus vt, and thus dy is dx. So we get minus m alpha, maybe not the minus, I'm just going to put the constants, m alpha h bar squared, integral of minus infinity to infinity of e to the minus 2m alpha, absolute value of y over h bar squared dx. Okay, and now how can we solve this? There's a few ways. This has an absolute value. How do we deal with integrals that have an absolute value? What we have done previously is something that's very good, and we separate the integral. We say, okay, since the absolute value has two different possible values, so absolute value of y, this is minus y if y is smaller than 0, or y if y is greater than 0. So we separate the integral from minus infinity to 0, where this is going to have the value of minus y. So we get e to the minus 2m alpha times minus y, so we get a plus, y over h bar squared dx. And then we have the integral from 0 to infinity of e to the 2m alpha y over h bar squared dx. And these integrals are now easy to solve. They are simply an exponential, right? So we get m alpha divided by h bar squared, and then e to the 2m alpha y over e to the minus 2m alpha y divided by h bar squared dy. Oh, I wrote dx here. That, of course, makes no sense. Dy. And same here. That makes no sense. Dy. Okay, so now the first integral, right, this is simply an exponential. So what we get is the same constants here. And we integrate the exponential, so we get e to the 2m alpha y over h bar squared. And we get divided by 2m alpha divided by h bar squared, so that multiplies. And then this has to be evaluated between 0 and infinity. But at infinity, this part goes to, okay, no, it's not 0 and infinity, sorry, it is between minus infinity and 0. So at 0, this part will be 1, so the exponential will be 1, and then at minus infinity, it will be 0. So this thing is simply h bar squared divided by 2m alpha. And then we have the second integral, this one, which is plus, and now we get, because we have to take the integral, we get a minus sign. So it is minus e to the minus 2m alpha y over h bar squared divided by 2m alpha divided by h bar squared, which goes up. And we have to evaluate between 0 and infinity. But at infinity, the exponential goes to 0. And at 0, the exponential is 1, but we get a minus sign in front, right? Because it is minus that thing evaluated at 0. So there we go. We get this. And notice that this cancels out. Then m alpha cancels out. And we get 1/2 plus 1/2, which is 1. So our integral is indeed normalized. So this integral right here, all of this, this is 1. Now, what about this integral? So I'm going to make some space, make some room down here. Oh, I messed it up. Let me get rid of that. And now, this integral, right? Okay, we haven't really gotten to this part, so I guess we have to be careful not to forget about it. So I'm just going to call this I1. So I1, what is it? Now, we can use a change of variables again. So we have 2 times integral, and now let's say y is equal to x minus vt, just as before, and thus dy is dx. And the lower limit, right, when x is vt, means that y is equal to 0. So now our limit goes from 0 to infinity. And this is going to be m alpha h bar squared e to the minus 2m alpha, and then absolute value of y over h bar squared dy. But we are in the region where y is positive, so we don't need the absolute value, right? It is the same. And this integral we already solved, so I'm just going to do it right away. And we literally just solved it. So this is m alpha over h bar squared times, and then we get h bar squared divided by 2m alpha. So this thing, this is like that, this is 1, right? So this entire integral is 1. So we get 1 minus 1, which is 0, right? So bam, this entire thing is 0. So we are only left with this integral right here. But this is a constant, right? So this thing is e plus 1/2 mv squared. And then we have integral from minus infinity to infinity of our density squared, which we know is 1 because this is normalized. So the expectation value of the Hamiltonian is this. And as you can see, the expectation value of the Hamiltonian is the energy of the bound state plus the kinetic energy that the group of the waves, right, the wave packet has. So that is, very interesting. And that is what one expects, since the delta function is moving as well. And basically what the delta function is doing is that it is dragging the bound state along, right? So as the delta function moves, our wave moves alongside it, right, with same velocity. So that is a very interesting conclusion. So there we go. I can't find this. We have now found the expectation value of the Hamiltonian. So yeah, we are now done with the problem. And as you can see, this wasn't really anything new. It's the same procedure as we have done before. Simply plug everything into the Schrodinger equation. And we did have to know how to work with the step function. But other than that, it was relatively straightforward. So I hope that this was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe. And if you really enjoy the content, maybe consider checking out my Patreon. So I'll see you in the next video. Thank you very much for watching.